Welcome to this module, and in this module we will look at analog to digital converters. So, what are types of ADCs and how does it function? Okay. So, there are 4 basic types of ADCs that we will look at. The first one is called flash ADC, then we will talk about sigma delta, followed by dual slope, followed by successive approximation. So, let us see flash ADCs. The flash ADC or the flash method utilizes comparators that compare reference voltages with the analog input voltage. When the input voltage exceeds the reference voltage, a high is generated. Comparator is not needed for all zeros condition. We will see in the next slide how the circuit looks like. In general, a 2 raised to n minus 1 comparators are required for converting a n bit code. The advantage here is that it provides a fast conversion time because of a high throughput, and the disadvantage is large number of comparators are necessary for a reasonable sized binary number. For example, if you see this circuit, you can very easily see how many comparators are required for 8 bit converter like C1, C2, C3, C4, C5, C6, C7, 7 comparators, right. So, this is how it actually works. So, you have a reference voltage, you have an input from sample and hold circuit, and depending on the reference voltage and input voltage, if the reference voltage is higher than input voltage, then you have 0 at the output. If the input voltage is higher than reference voltage, you have 1 at the output, and that goes to the priority encoder, and that is finally converted to your parallel binary output, right. So, there are enabling pulses to the encoder, there are op-amp comparators, and there are input from sample and hold. Let us see here. So, the flash method utilizes comparator that compare reference voltages with analog input voltage, like we discussed. When the input voltage exceeds the reference voltage for a given comparator, a high is generated, right. So, input voltage, because it is connected to the non-inverting terminal, so high will be generated or 1 will be generated. The reference voltage for each comparator is set by the resistive voltage divider circuit. You can see here the reference voltage. So, this is nothing but a resistor R1 and R2, and if you apply voltage, the voltage divider circuit. So, same way you keep on dividing the voltage until here, and that is how the reference voltage are set. The output of the comparator is connected to an input of 8 bit primary encoder. This is a primary encoder which is 8 bit or 8 input primary encoder. The encoder is enabled by a pulse, and a 3 bit code representing the value of input appears on the encoder's output. Here is the output that is appearing at the encoder's pin 1, 2 and 4. The binary code is determined by highest order input having a high level. Now, assume that the step size of 1 volts, the voltage divider sets up a reference levels from each comparator, so that there are 3 levels corresponding to 1, 2, 3, 4, 5, 6 and 7. The analog input is connected to other input of each comparator. Now, you understand this question. So, with analog input less than 1 volt, all 7 comparators will be low. What we are saying is, if you have step size of 1 volt and the voltage divider is set for all comparators, so it is 1, 2, 3, 4 until 7, then what will happen if the analog value, that is the value from the signal, is less than 1 volt, what will happen? All the comparators would be low, right. So, output will be 0. Suppose the analog input is between 2 and 3, then comparator C1 and C2, right, will be high, and the priority encoder will respond to high of C2 and produce a binary of 0, 1, 0. So, this is how the comparator works. This is how in general your flash ADC will operate, and if you want to determine the binary code output of 3 bit flash ADC and the encoder enable pulses are as shown below, then assume V reference voltage equals to 8 volts. If you have this particular signal, right, you can see here there is an analog signal and there is an enable pulses. So, suppose you are asked that the resulting digital output sequence is 100, 110, 111, 110, 100, 010, 000, 001 and so on until here. Waveform of the resulting digital output sequence, draw it. So, it is very easy. If you really see, you have to draw pulses, and for each pulse you have to show a particular signal. For the first pulse, what is it? 100. So, if you have here 3 bit flash, right. So, you have D2, D1, D0. So, 100 is given by D2, D1 and D0. So, 100, right, 2 raised to 0, 2 raised to 1, 2 raised to 2. So, 100 will give us 4, right, that is here. Now we have second pulse. So, so when you have first pulse only D2 should be on, D1 should be 0. Second pulse is 1 1 0 1 1 0, that means D2 and D1 should be on, which is right over here and D0 should be 0. Third pulse is 1 1 1. So, all three signals 1 1 1 should be high. 4 pulse is 1 1 0. So, it will be 1 here, 1 here and 0 here. It is very easy to draw. Very easy to draw the waveforms of the resulting digital output sequence. Now, this is the flash DAC, but if you flash ADC, but if you want to understand the another kind of ADC, which is a dual slope ADC, let us see how it works. So, a dual slope ADC is a common in digital voltmeters and other type of measurement instruments. A block diagram of dual slope ADC is shown right over here, where it consists of the analog input signal, there is a switch, there is a integrator or ramp generator, and there is a comparator with a control logic. There is a switch which is connected to the to this block, right, through a control logic, and then you have a clock, you have a counter, you have latches, and finally you have the binary output. So, this is a block diagram of dual slope ADC. Suppose people ask, or if in exam you are asked what kind of dual slope ADC block diagram looks like, you can draw this very quickly. Assume that the counter is reset and the integrator output is 0. Okay. So, if the counter here is reset, right, counter is reset and your here counter is reset and your integrator output is 0, right. So, a positive input voltage is applied to the input through switch. So, here we are connecting switch to the positive input voltage, and then since the inverting input of A1 is at virtual ground, and assuming that Vin is constant for a period of time, there will be a constant current through the input resistor and through capacitor, correct. So, it will be a constant current through input resistor and capacitor. When you connect these 2 plus V in, capacitor will start charging linearly because the current is constant, and as a result there will be a negative going linear ramp on the output A1, correct. Now, when the counter reaches a specified count, it will reset and the control logic will switch back the negative reference voltage to input of A1. In that case, what will happen? At this point, capacitor is charged to negative voltage proportional to the input analog voltage. So, now the capacitor discharges linearly because of the constant current from minus V reference. So, now the capacitor has to discharge and have a constant slope that is independent of charging voltage. So, one is capacitor charges, then the counter resets and the capacitor starts discharging. As the capacitor discharges, counter advances from its reset state. The time it takes from capacitor to discharge from 0 depends on the initial voltage minus V. When it reaches A1 reaches 0, A2 switches to low state, right, because A1 reaches to 0, A2 will reach to low state, and disables the clock of the counter, which is if it is low, the clock will be disabled, and if that is the case, the binary count is less, thus completely one conversion cycle. The binary count is proportional to voltage V in. Now, this whole process is illustrated right over here, right, where initially the capacitor is charging when your counter up to n and then it resets, and then it is sent back. It when it is connected to plus V in, it is charging. When it is connected to ground, then at some point it, because of the when the reset signal is sent, it will start discharging, capacitor will start discharging. This will cause the change in the output signal. Now, if you have understood the flash and dual slope ADCs, let us see successive approximation ADC. Successive approximation ADC, the block diagram is shown here, where it has a digital to analog converter, it has a SAR, it has a digit and clock, and it has the serial binary output. It is connected, the signal which is a digit connected is to the output of the comparator, and we have a parallel binary output from D0 to D3. Now, the input bits of DAC are enabled only one at a time, starting with the most significant bit. Okay. And as each bit is enabled, the comparator produces an output that indicates whether the input signal voltage is greater than or less than the DACs. You understand this thing, if the V out here and the initial input here, so if it is more than DAC or less than EAC, we can easily see with the help of comparator. If the signal input is more than DAC, then we can have a higher bit. If the signal input is less than VAC, we can have a lower bit, right. So, the input of the DAC are enabled one at a time with MSB. At each bit is enabled, comparator produces an output that indicates whether input is greater or less than the output of DAC. If the DAC output is greater than input signal, the comparator output is low, causing the bit to the register to reset, right. So, we send here a digit called reset. Now, if this DAC output is less than input signal, then bit 1 is retained in the register. Now, this is of course a register which is shown here, and the system does this with the first MSB first and then next right of, we start with MSB and then this one and then this one and finally comes to the LSB. Okay. After all the bits in DACs are tried, the conversion cycle is completed. So, this is V out 8 bit volts for 2 raised to 3. You can see here, assume that DAC the following characteristics, you can very clearly see for plus 5.1 volt, plus 5.1 volts is given. Now, if you have here 8, then 8 volt is greater than 0. So, low is sent, right. So, now it is sent here. So, when you apply a clock, you have 1 0 0 0, but if you have for 6 volts, right, then what will happen? Here is still is more than 5.1. So, again a low is applied and you have if you send the signal, then it will be 0 1 1 0, right. So, 1 1 0 will be the value. Same way if you go for 4 volts, then in that case 4 volts is less than 5.1 volts, that is why it will be high bit, and you can have here 0 and then 1 and 0 and 0. This will be in your register, which is the value you have to keep. Now, in this case, if you see if there is a low value, then you have to reset this value. If there is a low value, you have to reset this value, but if there is a high value, then you can keep this value. Same way here, 5 volts is less than 5.1 volt, you can keep the last significant bit, which is or least significant bit, which is 2 raised to 0, right. So, 1 volt for 2 raised to 0 bit we can retain here, right. 2 volts for 2 raised to 1 bit we can see here, and similarly. So, it is very easy to understand the DAC ADC characteristics and DAC characteristics. Now, this is how the operation works. So, just to look at the slides in detail, you can see very clearly. Let us take one example or let us take this example where step 1 you have 2 raised to 3 ms bit, which is your most significant bit, and the output of DAC is 8 volt. Since this is greater than 5 volts, the output of the comparator is low, causing the MSB of SAR, which is successive approximation register, to reset to a 0. Now, step 2 is 2 raised to 2, which is bit 1. So, output of DAC is 4 volts, which is less than 5.1 volt. In that, the comparator switches to high, causing this bit to retain in SAR. Similarly, step 3, if it is 2 raised to 1, which is 1 volt, then output of DAC is 6 volts. Since this is greater than 5 volt, the output of comparator switches to low. So, it is very easy, right. If it is more or less, that is what we are comparing. Nothing so difficult in this particular ADC. Now, the final one would be SigmaDelta ADC. So, what exactly SigmaDelta ADC means? This method is based on delta modulation, where difference between two successive sample is quantized. The output of delta modulator is single bit stream, where the relative numbers of ones and zeros indicate the level of amplitude, right. So, how many zeros are there, how many ones are there, and the number of ones over a given number of clock cycle establish the signal amplitude during the time interval. Now, here the maximum number of ones corresponds to maximum positive input voltage, and number of ones equal to 1 half the maximum corresponds to input voltage 0, right. So, 1 half will correspond to 0, only 1 will correspond to high. Number of 1 correspond to maximum negative input voltage. This is illustrated in simplified way in this particular figure, as you can see here. 20481, 40961, these are all zeros. When zeros, it is minus negative. If it is 1, it is plus. If it is in between, then it is considered as 0. So, if you see this particular ADC, right, which is our SigmaDelta ADC, then this is the block diagram where you have the integrator, a quantizer, n bit counter, latch, and output of the 1 bit quantizer is fed back to the 1 bit DAC, which is sent to the summing point, where the summing point will look at the signal sent by 1 bit DAC and analog input signal, and the error is fed to the integrator. So, that is what is written over here, and a different signal output of the sum is integrated and 1 bit DAC increases or decreases, the number of 1 depends on the different signal. This action attempts to keep the quantization signal, that is feedback, equal to incoming analog signals. The single bit data stream is converted to as a series of binary codes. The counter counts ones in the quantized data stream and code in the counter that represent the amplitude of analog signal for each interval. So, the point is the most easiest way of understanding DAC or ADC is when you use it. Until you use it, you guys will not know how to operate these ADCs and DACs. Okay. So, what I think what we have learned in this particular module is what kind of ADCs are there, and we are just if you have really see, we have kind of run through that ADCs. The reason is that we have to use these ADCs. The detail of how the ADCs are operated is good to understand, but how you can use it is more important. Alright. So, I leave it on you how you read it further, how you understand it further. If you are confused, do ask me, anytime you can ask me, but if you know how and where to use ADCs and DACs for a signal conditioning system, that is where the real application lies in. Because when you design an electronic conditioning system, you need to know what kind of circuits you have to use, right. At what point your ADC will come, at what point your DAC will come, at what point your filters will come, at what point your amplifiers will come, at what point your integrator and comparators will come, at what point your sine wave and this kind of frequency generator signals will come, at what point you have to interface your sensors to your electronic conditioning system, and at how you can convert this data to a display. So, this everything in some sort, when you bring it together, you can design a complete system. And through this particular modules, what I have tried is to help you out or to share with you how to apply or use operational amplifier in real life scenarios, in the practical applications, and in that when you see the block diagram, when you further go and see the circuit diagram, then you will see that where exactly this kind of circuits are used. Okay. So, you just go through it once again. If you have any doubts, feel free to ask me, right. Till then, you take care.